let's talk about a type of computer that doesn't just calculate faster, but, well, it fundamentally changes the rules of what's even possible to compute. Today, we're going to pull back the curtain on the strange, powerful, and kind of mind-bending world of quantum computing. So you might be wondering, why do we even need this? It's because some problems are just so ridiculously massive that even our best supercomputers would just give up. They'd grind away for thousands of years. Think about trying to perfectly simulate a single complex molecule for a new drug. For challenges like that, being a little bit faster just isn't going to cut it. We need something entirely new.
All right, here's our game plan. First, we'll get a handle on this whole new computing paradigm. Then, we'll dive headfirst into the weird world of qubits, the building blocks of this new reality. After that, we'll see how they're pieced together, explore the incredible real-world applications, and finally, get a reality check on the huge challenges that are still ahead. So let's start with that new paradigm. Look, this isn't just about making a faster chip. It's about building a machine that operates using the native language of the universe itself, quantum mechanics. This table really cuts right to the chase. Classical computers use bits, simple on or off switches, a 0 or a 1. They do one thing at a time, sequentially. Quantum computers, on the other hand, use qubits. And thanks to the wild rules of quantum mechanics, a qubit can be a 0, a 1, or, get this, both at the same time. This is what lets them explore a staggering number of possibilities all at once. So, if qubits are the secret sauce, how in the world do they actually work? To understand that, we've got to take a little trip into their weird and wonderful world and get to know the quantum toolkit that makes them so powerful. And the absolute star of the show is the qubit. Unlike a bit, which is just a simple light switch, on or off, a qubit is more like a dimmer dial. It can be at any position, a mix of on and off, all at once, right up until the moment you look at it. This power of both has a name: superposition. It's what allows a quantum computer to chew on so many calculations at once. Imagine a regular computer trying to solve a maze. It has to try every single path one by one. But a quantum computer using superposition? It gets to explore all the paths simultaneously. It's a total game changer. Probably the most famous way to wrap your head around this is Schrödinger's cat. You know the one. He imagined a cat in a box with a poison that might or might not be released. And until you actually open that box to check, that cat is in a superposition of being both alive and dead. It's only the act of measuring, of looking, that forces one single outcome. Qubits work on that exact same bizarre principle. And if you thought superposition was weird, brace yourself for entanglement. Einstein famously called it spooky action at a distance. When you entangle two qubits, their fates are linked instantly. You can measure one, and you will instantly know the state of the other, even if it's on the other side of the galaxy. It's not communication, it's just this deep, weird connection they share. Okay, so we have these totally mind-bending concepts. How do we actually build something useful with them? Let's take a look under the hood at the machinery that puts these quantum principles to work. It's kind of like how classical computers have logic gates, and or not gates. Well, quantum computers use quantum gates. These are basically the tools that let scientists carefully poke and prod the qubits, push them into superposition, entangle them with each other, and steer the whole computation towards the right answer. So a quantum computation usually boils down to these 4 steps. First, you get all your qubits lined up in a simple starting state, like all zeros. Then you hit them with a sequence of these quantum gates to create that complex state of superposition and entanglement. And this is where the magic happens. Through a process called interference, the probabilities of the right answers get amplified, and the wrong ones just cancel each other out. And finally, you measure the system, which forces everything to collapse into a single classical answer, zeros and ones that we can actually read. All right, all this complicated physics has to be for something, right? So what's the point? Why does this all matter? Let's look at the incredible real-world problems that quantum computers could finally crack. And the potential payoff here is it's just transformative. We're talking about designing new life-saving drugs by perfectly simulating molecules, something that's literally impossible today. Or, completely revolutionizing finance with risk models that could actually work. And then there's this huge cybersecurity paradox. Quantum computers will likely be able to break the encryption that protects our entire digital world, but they'll also give us the tools to build new, truly unbreakable codes. Now, it's super easy to get carried away by all the hype, but
But it's so important to understand that building a useful quantum computer is one of the single greatest scientific and engineering challenges of our time. So let's get a little reality check.
It's the obvious question, isn't it? If this technology is so revolutionary, why isn't it everywhere? Well, the simple answer is that the quantum world is unbelievably fragile. These right here are the enormous hurdles engineers are fighting every single day. Qubits are, well, they're divas. The slightest little disturbance, a tiny vibration, a flicker in temperature, can make them lose their quantum state. That's called decoherence. It leads to really high error rates, and to do anything truly world-changing, we're going to need millions of stable qubits, not the few hundred we have today. Oh, and on top of all that, most of these systems have to be kept colder than deep space. To track our progress, it's really important to get this distinction. We've actually already hit a milestone called quantum utility. That's where a quantum computer solved a very specific problem that a classical computer just couldn't brute force. That was huge. But the ultimate prize, the real goal, is quantum advantage. That's when a quantum machine is better, faster, or cheaper than any known classical method for a truly useful problem. We're not there yet, but we are definitely on the path. And you can actually see that path laid out on public roadmaps from companies like IBM. But notice the shift here to logical qubits. This is so key. A logical qubit is basically a super stable, error-corrected qubit that's built using lots of noisy physical ones. The goal isn't just a higher qubit count, it's about building more robust, more reliable systems that can run the ridiculously long and complex algorithms we need for a breakthrough. And this brings us to a critical, maybe even a little scary question. One of the very first quantum algorithms ever designed, Shor's algorithm, can theoretically break the very encryption that underpins our entire digital society. Now, the machines that can run it aren't here yet, but they're on the horizon. So the race is on, not just to build a quantum future, but to build a digital world that can actually survive it. And that's a challenge every single one of us has a stake in.